talk. There will be two, one by Huckleberry from graphics, and Gerald Schwartz from Brandless. And just wanted to say that Alan and I both have bachelor's degrees from Yale University. It's an important thing. There aren't that many others. So Alan's title is On the Complex Geometry of Flag Domains.
So, I'll make some small, rather classical remarks here. I'm an organizer of this conference, but if you want to convince me that since it was a workshop for students and so on, I should give some introductory remarks, and also something about some of the work I've done in the last years. So, didn't have the energy to correct to this notation, which I should have. So I had the following notation here: flag manifold G mod B. The real form is G0, so this is the real form like GS. And as you know, G0 has finite many orbits on, only finite many orbits on Z, and so there are open orbits, and any one of them will be called a flag domain. And here's a rough outline of what I'd like to talk about, and really focusing on one type of object in these flag domains, which I'd like to call a cycle. So this, in the talks yesterday, this is the closed K orbit, which you will find in any open orbit. It is unique. Let me comment on that in case you haven't thought about it. There's something called multi-vibration, which realizes a domain like this is a vector bundle, a vector bundle which is equivariant with respect to the compact group over the minimal compact orbit of the compact group. And in this case, this minimal orbit, which is really the minimal dimensional theoretic orbit, is complex. I call that a cycle. And the first small remarks will be a discussion of cycle connectivity. You can guess what that means. The possibility of connecting 2 points by a sequence of cycles, wherever these cycles are. These are compact varieties, and we would like to connect 2 points by natural compact varieties, and relation to the concept of holomorphic convexity, which is a complex analytic concept. Then I would like to try to explain, this is something that goes back to Professor Schmidt's thesis, is how these cycles really are generating cohomology in the same degree as their dimension, and how to transform somehow this cohomology of the domain D to the function theoretic level using Schubert theory of the cycle space. So that would be one of the important parts of my talk. And I've used this conceptually for several years, for many years in fact, but never really computed the Schubert theory here. And now I want to really use it in detail where the computations matter. And so this is the project of Anna Birkan's thesis. I think you met Anna, some of you. And I will not comment on the details of that theory, but I will tell you what it's about. And one of the uses of this trace transform is to prove that the cycle space, I'll tell you what this is, the cycle space, the space of all relevant cycles, is actually, carries a negative curve metric. And this in particular means that it's hyperbolic in the sense of Kobayashi. But what it really means is, for us, that the automorphism group is a D group acting properly in space. And I will mention with some examples that you can't expect that in general at all about the So finally, I will comment in detail on the automorphism group of cycle spaces and its relation to the automorphism groups of the flag. So that's roughly what I have in mind today. So I'd like to introduce a nice example I like very much that I think fits in this workshop, how these cycles these domains appear and what these cycles can be in these domains. So, what's happening? What could happen?
On, off, or up to?
Not going to do nothing works. So we should have anyway. Yeah. I want to log in on the end. Sorry. So there are a number of papers here. Joe, Greg Orfels, and I wrote a research monograph which contains, particularly in part 2 of this, what I'm talking about today. And my recent remarks on this appear in these 3 papers. I think the last 2 are most relevant. If you're interested in the, so to speak, latent geometry of these domains and the relations to these Schmidt exhaustions, I talk about this in other contexts also in this paper here. So the example I want to talk about is, everybody has heard this word of K3 surfaces. What is a K3 surface? The easiest first example of a K3 surface is by the Kummer construction. You all know this from your function theory 1 lectures because you know the Weierstrass construction of taking an elliptic curve or a torus and modding out by plus minus the identity. This has 4 fixed points, but this does not cause a singularity in dimension 1. So this is just 4 fixed points, and the quotient is P1, and everybody knows about this construction. In dimension 2, you take a 2-dimensional torus, you mod out by plus minus the identity, you get 16 fixed points, a half lattice points of the lattice. And they are serious singularities, but you can desingularize them with a very well-known growing up, which yields over each singularity a rational curve with a self-intersection -2. -1 would be smooth. This is the first non-singular, non-smooth example. After doing that, you get simply connected surface. Surface here is a complex surface which is a polarity surface. You can actually push around and really see in concrete detail the physical area. And of course, if the torus you started with is algebraic, this is algebraic, which has a lattice that you know about here, namely 3 times the hyperbolic plane plus 2 times EA. By the way, 2 times EA is 16, and these are the 16 curves that you got by blowing up these singularities. And you have this lattice, and why is it a lattice? Because from H2 you have cup product. And so it's just simply the intersection product on H2. And then in general, this is just an example, there's a sequence of examples here. In general, the way to look at these surfaces is this. You have a pair, it's related to the talk this morning, where X is holomorphically symplectic. So it's very easy to see in this construction that there's a nowhere vanishing 2-0 form here. So that would be holomorphically symplectic. Doing symplectic geometry over the reals, there's nothing to say about 2-0. There's a holomorphic 2-0 form here. And in fact, it's enough to characterize these manifolds in a good way to assume that the first Betty number is 0. They are in fact simply connected. Okay, so a pair then, a marked K3 is a pair X phi, where phi is some isomorphism, is a choice of isomorphism of H2 to this fixed lattice. Okay. Now we come to, I think, something close to the discussion this morning. How would you like to parameterize these things? Yeah. So that's what he was talking about. The founders of these things, I would like to write down all of them now. And I underline, if you haven't had experience with this, writing down all complex structures on one real manifold is a very big job. You almost never can do this. You have to have some additional information. In this case, it is the marking. So we extend this marking to the second cohomology, so just a complexification of the lattice. And then the second cohomology, this is what we heard about this morning. In this case, because it's a surface, even if you don't know too much about polarianity and so on, we have this decomposition, the Hodge decomposition in this case. In fact, these surfaces are all Taylor, but that's a deep theorem. So this splits up in 2,0, H11 and H02. And in fact, H20, there's a nowhere vanishing holomorphic symplectic form. So H20 is generated by this, it's one-dimensional. And you have a map. And the map is, you associate to every pair this line in this space. However, by the isomorphism that you've given to the fixed vector space. As X moves around, without any isomorphism, you don't know where to go. So you need to map this into a fixed space. So this is this line in this fixed space. Classically, this is called the period map. So it's a map from marked K3 surfaces, the set of marked K3 surfaces, and you check very easily that this is an isotropic line, so it goes into a quadric. So this space, you land into a quadric. This lattice is a lattice, well, you know what it is, I told you what it is, but the real group here, the lattice structure here, you see down below, is 319. So in fact, most of the 19 is in the H11 part. So you have, okay, so there's the 319, and what you land in is the set of positive isotropic lines in the 20-dimensional part. So given a marked K3 surface, you have a map, you have a point in that flat domain. So that's an open orbit of SO 319. I wrote plus because otherwise it's not connected. Okay, so there are many problems here. Some people call this Torelli problem. So the first question is injectivity, and this is yes. The second question is surjectivity, and this is yes. And this is a long history of beautiful mathematics, starting with one of my teachers, undergraduate, and older people, and ending rather not so long ago. So it's a beautiful example of how something, not quite in the exact context of the lecture this morning, but something you might call a Hodge theoretic situation, where you have a beautiful parameterization of very beautiful, very important surfaces by a flag domain. Now, in this flag domain, you take a look, the real form is SO319, so the maximal compact you first see in there is, of course, SO3 cross SO19. Yes, there are many, they're all conjugate, but you see this at first. So you study the orbits of this, and you find out that there's a unique orbit of minimal dimension, which is complex, and it's simply P1 in this case. It is the simplest possible positive dimensional complex manifold you can think of. It is P1. And in fact, actually, in the modern theory of so-called Calabi-Yau metrics, there are very special P1s here that have a very good metric meaning in these terms. These manifolds are hyperbolic. So if you look at it carefully, there will be three structures on such a manifold, I, J, and K, almost complex structures. And then you look at linear combinations of AI plus BJ plus CK. And of course, A squared plus B squared plus C squared should equal 1. And you see that you're getting a two-sphere. And so these two spheres here, some of them are very much related to these beautiful hyperbolic structures. We call those lines Yau lines, because to understand these lines, you really need to know the existence of a Calabi-Yau metric. So it's very close. Now, I would like to look at the general setting here. So, for me, let me now say something in general. Let D be a flag domain of a real form G0. Choose any maximal compact K0. It has a minimal orbit which is complex, in fact complex. It will be Q-dimensional. So Q is the dimension of this complex orbit. And now you look in the cycle space of all Q-dimensional varieties in Z. What is the cycle space? A point in the cycle space is at first a formal linear combination with positive integral coefficients of compact irreducible varieties which are Q-dimensional. So N1 C1 plus N2 C2 plus NK CK. If the NI's are positive, you don't want to look at negative things. You want something that really occurs as a multiplicity when you move a cycle and physically move a variety As you know, if you have a quadrate, for example, you move this quadrate, it may degenerate into two lines. That's okay. So that's 1 times the first one plus 1 times the second one. But then they may degenerate into 2 times one line. Now, somebody may call this the Chow scheme, and I call this Barlet space because I very much use the point of view of Barlet and a more analytic point of view to this cycle space. So this infinite dimensional space is locally finite dimensional. Its components are finite, irreducible components are finite dimensional. And what we then look at the cycles that stay inside of D. Because we're interested in D, we start with the base cycle, that was this K0 orbit, and we think of all possible other cycles there. And we don't want this infinite dimensional space, so we check that at the base cycle, it is smooth. This is a hard piece of work, it's a cohomology calculation. The base cycle is a smooth point of the cycle space. It doesn't have 25 irreducible components coming out of it, so what we can do is we can say, just take the irreducible component of the cycle space, which contains this point, and the irreducible component makes sense because it's smooth. Okay, so the notation I use is CQ of D is the irreducible component. The connected component, some people call this MD. Joe Wolf started calling this MD. I don't know, I think he thought this was a moduli. These cycles are all the same. They do not change in their complex structures. They are all the same manifold. In the case of the K3, you have all the same manifold. Now, one thing you can do is push these cycles by the complex group until you leave the domain, and then you stop, and that's it. You can prove that that's what we call MD. You can prove that if you push by the complex group, and then see what happens when you intersect back with this domain. In fact, that is still closed in this cycle space. It's a very useful technical remark. And much is known about this, as I said, much we wrote about this, our research on graph and many other people have contributed. It's a very important thing, but I want to emphasize the cycle space is, in general, much bigger. So it is much bigger than just pushing, and not only is it much bigger quantitatively we know exactly, this is part 3 of this monograph, we know exactly, here's the pushing, here's the submanifold that you get by pushing. We know the normal bundle, and of course the isotropy is the stabilizer of that manifold. So we're pushing this manifold around as a stabilizer. It's a reductive group, so the tangent space splits there, and we know exactly the representation on the transversal space. So we know not only how much bigger the cycle space is, but we know in terms of representation theory what it is. So infinitesimally we know a lot, and we do not know everything. So this basic dichotomy, that I like to call it basic dichotomy, which arises from this theory. As you know, the maximum principle tells you that every holomorphic function is constant on the cycle, on the base cycle. You start moving the cycles around, they're constant on every one of those. But you may be lucky that you have non-constant functions. I remind you that a Hermitian symmetric space of bounded type, it is a Stein domain, so it's holomorphically separable. And this is one of these domains, so there are lots of examples. But in fact, all examples are Hermitian, where you have non-constant functions. And not only that, the non-constant functions come from somewhere in a very organized way. There's a fibration of the ambient manifold, G mod, let's say G mod P down to G mod Q, which the base, if you push down what happens to the flag domain, the flag domain is a Hermitian symmetric space, a Stein manifold, and all the functions, of course, because it's a fibration, it's a saturated fibration. So the fibers in the flag domains are the cycles, actually. So in this case, the cycle space is the Hermitian symmetric space, and the holomorphic equivalence relation, 2 points are equivalent that every holomorphic function identifies, is really just this projection. Now, the Hermitian symmetric space is topologically trivial and a Stein manifold, so that's a trivial product. So this is almost, you have to say, a very simple situation. If you have non-constant holomorphic functions, then the obvious equivalence relation, modding out by the constant holomorphic function, so to speak, just gives you a product of flag domain as a Hermitian symmetric space. And by definition then, well, no, not by definition. The third property is D is not cycle connected. Now I want to talk about this because this is very much related to misconceptions of understanding Griffith's theory. In this case, please consider what I just said. Here's the Hermitian symmetric space. Let's say it's a ball. And your domain is someplace over it, which is fibered by it's a fiber bundle, but it's really a trivial bundle of compact fibration onto the base plate. In this way, the fibers are exactly the cycles of the cycle space. There are no more. That's it. Now, there are other domains that are extremely important for this Hodge theory, where you have fibrations of the cycles, but the base space is totally real. Okay? So you have yeah? And there will be many, many more cycles which you can move in your domain, but there's no contradiction. Do you understand? If you move a cycle, if you have a bounded domain here, which is Stein manifold, and you move a cycle a little bit and look at its image, it's a compact manifold in a small domain, so it has to be a point, right? But if that's just a map onto a real parameter space, this happens in the non-Hermitian case all the time. Yes? And so it's a sort of a warning that there are beautiful families of these cycles, but they're parameterized actually by the real points of the cycle space. This manifold you will get downstairs in those cases, there will be an involution on the cycle space, and that will be the real points of the cycle space. Okay? So, in that case, when you get that situation, you can move cycles all over. So the definition of cycle connected is given 2 points. There's a chain of cycles which is connected, which goes from one to the other. Okay, that's the dimensional algebraic geometry. That's the standard. So this is the basic dichotomy. Either you have this trivial situation, or it's cycle connected. So everything I will really focus on in the rest of the talk is I'm very much interested in the case where it is cycle connected. It's the most interesting case right now. However, the tools that I will talk about are completely general. Now, I will spend 10 minutes discussing this beautiful picture you got on a So she sent me the program for this picture. And I couldn't, it's so big I couldn't get it to work. So I just copied it. I copied the picture. Okay. So let's just start to talk about this picture. So, the real group action on the flag manifold, the flag manifold is the whole family space. The real group action is real algebraic. And so the boundary, whatever boundaries there are real algebraic varieties. So these boundaries what I drew here are very nice. It's not like Cantor sets appear or all sorts of wild things. These are very nice things. I am also, as a complex analyst, interested in the curvature of these boundaries from a complex analytic point of view, which is interesting. There are exhaustions of the flag domain, which send back to Luber's thesis, where I have computed explicitly these exhaustions. And what happens is, the boundaries in Levy form, this is the complex analytic curvature form, degenerates. It tends to flatten out at the boundary, whereas inside it's much better. Anyway, the boundaries look like that. The only thing that's not too good about Anna's picture is the gray thing in the middle. That's supposed to be the cycle. Okay? She wanted to make it look like a sphere, but then when it started looking like a sphere, it got too messy. So think of that as somehow like there's the diagonal of the sphere. Think of that as something like it's a submanifold. It's a flag manifold. It's an orbit of K0, which is a flag manifold. There it is. Now, years ago, when I started trying to analyze this thing, I realized that the way to try to parameterize the cycles in a completely stupid way is try to find transversal varieties. This makes sense. And somehow transversal varieties should be parameterized in these cycles.
The intersection points with the transversal variety should be the coordinate on that transversal circle of the cycle. Now, after years of fooling with matrices, I finally understood what to do. And we take any Iwasawa decomposition, where K0, any K0, A0, N0 decomposition of G0. So K0 is fixed in this discussion because we have the base cycle. Take any Iwasawa decomposition and take any Borel containing A0, N0. Now there are many reasons to take those kind of Borels. One, you can just say, these are the best Borels from the point of view of the real structure. Right? Because that's one way of thinking about it. These are the Borels that correspond, that have fixed points on the closed, they can be characterized as those Borels that have fixed points on the unique closed G0 points. This is also a very natural characterization of those Borels. So, for no better word, I call these Borels, let's not introduce absurd notation. Then I consider Schubert varieties of these Borels. So one of my goals was to understand topologically the cycles and understand analytically the cycles by transversal slices. So I'm interested in good Schubert varieties that intersect these cycles in good ways. So I take good means here defined by Borels which contain A0, N0 factor of an Iwasawa decomposition. I call them Iwasawa-Schubert variety if it is of complementary dimension to the cycle. So it should be n minus q dimensional. And that's it. And intersects the cycle. So some will intersect and some will not intersect. Okay? The theory is, and it's not so difficult to prove, that if the subject Schubert variety, that's the red thing S, intersects the cycle, then it intersects infinitely many points and at each point transversally. So the intersection number is really 1 at each point. Now the funny thing is that the Schubert variety goes in and out and in and out and in and out, so it ends up intersecting in many points sometimes. I should tell you, Anna's really computed a lot of this. Sometimes many points, sometimes only 1 point. It's very interesting numbers. So the Schubert variety goes in and out, in and out, in and out. Now those of you who have dealt with Schubert varieties know that they are singular. So you would not be very happy if the intersection is at a singular point. However, it is a trivial observation that the complement of the open orbit, so now I'm going to go to this thing, so if S is equal to an orbit plus the complement of the open orbit, so the possible singular set, right? This singular set is outside someplace. For absolutely trivial reasons, it's just too small. It cannot go in here because I just can't. You would see immediately. So the singular set is outside, so that's very good news. This Schubert variety intersects this thing in the Schubert cell, and the remarkable news is, if you take the A0, well, it's probably not remarkable, but the A0, N0 orbit of each of these points is closed. There it is, unambiguous in green. It's closed. When this is the A0, N0.
Something's green, and now I see.
Yeah, A0, N0. There are four A0, N0 orbits here, and what you do is correct. These orbits are closed, they're open in the Schubert cell, which already is rather interesting, because the A0, N0 is a lot smaller than the Borel. They're closed in the Schubert, open in the Schubert cell and closed in this thing, and they intersect here at one point. So I call these things Schubert slices. They're perfect coordinate slices for the cycle space. Now, all of this is motivated by many discussions I have with Barley on what we like to call the trace transform. Now, if you take a holomorphic function, maybe my didactics is not good. I'm going to take let's be algebraic geometric here. Let's take a rational function which has poles on E. E is a divisor, so right? This is a candidate. Let's take such a rational function. And It's holomorphic except on E. And now let's take the fundamental class of this Schubert variety. Now, as you all know, if I intersect this Schubert variety with a cycle and get 4 points transversally, the integral of the fundamental class, let's stop for a minute. The fundamental class of the Schubert variety is a QQ form. It's a complementary dimension. The Schubert variety is n minus q dimensions. And so it's a QQ form. All right? And it's what was talked about this morning. I mean, if you integrate this over a q-dimensional variety, you get the intersection, right? So it's something like Dirac measure, so you just get an intersection. And in this case, you get the number 4. Okay? However, if you integrate f times this thing, this is another form which is just as good. You're getting the average of f over the intersection points of the cycle with the Schubert variety. Okay. Good. Now notice that this is a transform, a very simple-minded, you probably all know it, but it took me a while to understand it. A very simple-minded transform from these weighted fundamental classes, which are elements of the Q cohomology of the cycle space, right? Of the domain. So omega is a QQ form on the domain. F times omega is a QQ form on the domain. You integrate this QQ form on cycles, you get functions on the cycle space. So this is a very interesting transform from Q cohomology using the transversal Schubert varieties to get functions on the cycle space. And not only for, I use the sheaf of holomorphic functions here, this is true for any vector bond. So you can, instead of pulling up the universal family and pushing down by integration, which you would do in Penrose's theory, for example, here we have a very direct calculation, and I'm very interested in using honest concrete calculations to really understand what we're getting here. So this is a computable transform which gives you a big piece of HQD realized in H0 CQ. And so I just wanted to mention what Anna did, and if you're interested in the details, her methods, in my opinion, are general, but it's very hard work, so it's only been done for the real forms of SLNC. And so she answers the following, I wrote it in terms of questions, she answers the following questions: which Schubert cycles have a complementary dimension have non-zero intersection, how many points of intersection, and what are the coordinates of these intersection points. And interestingly enough, you know the 3 real forms. In comparison, SLNR, which you see is very far away from the kind of things, so it's, you really have to use, for example, it's not measurable in general, and it's very far away from some of the things we've been talking about in this number. But there's only one, essentially only one open order of SLNR, but the intersection number, the number of points in the intersection is something like 2 to the n. So the multiplicity is extremely deep. For SUPQ, the intersection number of every cycle is 1. And it intersects, we were very interested in talking yesterday, it intersects the cycle in very, very special points. Related to somehow other, the standard Borel substrate. You see, this is not the standard Borel, so it's not so easy to do. Okay, so she answers these questions in 3 cases. I think it's very nice work, so if you'd like. Well, I wanted to tell you some of the ways I use this method. And the first main way I learned to use this method is the method of incidence divisors. So I do the most obvious thing. Remember, E is outside the domain. So So the domain is contained in Z. And I'm interested in cycles that are contained in the domain. But E is outside. So if I think of moving in the universal family of the cycle space, I'm moving C, and I'm still in the domain, and I'm moving, and so I go over here, and then I eventually go outside over there. I will hit E at some point. Okay. And so I define HES as the set of cycles that hits E. Okay. The theorem 1 is this is a divisor. Well, it's a hypersurface, and it's a Cartier divisor. This is very important, so we have a line balance. This is a delicate point, because there are a lot of singularities going around here. So this is a Cartier divisor, so some power of this thing is really a line bundle. Q Cartier, so it's not really Cartier, so it's Q Cartier, but that doesn't matter, you just take a power. And you might hope that this is an ample line bundle. It is not in general for a given S. But of course, there are many S's, and so you have many of these incidence varieties. Of course, let's fix even an Iwasawa decomposition, so even for that you have many S's. And then, of course, you can move with the real form. So you have a huge flexibility of these incidence divisors. And you put them all together and build a line bundle on the cycle space of the ambient space. So this is a singular, but it doesn't matter too much, projective variety. And you built, by these intersection divisors, a line bundle there. And you just consider the mapping given to you by the line bundle. Okay? So this is some mapping. This is, of course, a G bundle, because the G acts here. Yeah? So this is a G bundle. So this is in space. We get a mapping here, by the way. This is a meromorphic mapping into the representation space, some G representation space, which is computable, of the full cycle space. This meromorphic mapping blows up and down outside of D. It is horrible outside of D. I can't control it. You can imagine, because this is where E and all the singularities apply. But essentially, in fact, the power of it gives an embedding of CQ of D. So you should think of using incidence divisors. You can embed CQ of D into a beautiful projective variety. And of course, these incidence divisors become hyperplanes, and they lie outside. So you can think of the cycle domain as being some domain with incidence divisors outside, which are hyperplane sections, and you can move them with a real group, of course, because it stabilizes the cycle space. So you start moving these and build a huge number of hyperplane sections, and building these, you can actually build a hyperbolic metric, so on the cycle domain, things that have poles on these divisors. Those of you who are not familiar with hyperbolic metrics, let's just remind ourselves of and take P1, take away 1 point, we have the complex plane, take away 2 points, we have C star. These manifolds are far away from being hyperbolic. The correct metrics of these are never hyperbolic. Take away 3 points. As you know, it's a non-trivial exercise to find out the universal cover of that manifold is the unit disk. And using the Poincare metric on the unit disk, which has negative curvature, you have every notion of hyperbolicity in P1. Okay? And this is very analogous. You see, we remove 3 points from P1, and we got a hyperbolic thing. Here we're removing a bunch of incidence divisors from some projective variety, and we get a hyperbolic. So it's a complete analogy. So let me mention here in the, I'm too fast maybe. Mention here some consequences. The first consequence is the cycle space is realizable as a domain in an affine variety, because it's the complement of an ample hyperplane. That's already very good. And many of us believe, and I can prove it in virtually every example, well, in all examples, but just a few, that it is a Stein domain. Now, let me comment on that since I do have a few minutes. We heard this morning about Professor Schmidt's thesis. It's very important. We observed that in a very natural way, you can build exhaustions on some of these domains. Nada. So, on any domain in G mod B, you can do it. I think this was your area of interest at that point. But there are many other domains, for example, in flag domains of SLNR, where we don't know how to do it. This has been generalized to what is called, Joe Wolf and Schmidt called measurable domains. This means you have an invariant volume form, which is, of course, a very reasonable assumption. If you have an invariant volume form, you can look at the Ricci form of that, or you can argue in various ways and get metrics. Well, you get two metrics. You get a metric on the canonical bundle of the domain, and you have a metric on the ambient bundle, canonical bundle of the manifold. Comparing these two things, these are bundle metrics, but the difference of these two things gives you a function on the domain, which is an exhaustion. So you can compute, and this, the optimal, well, you compute, and you can see that this function should have signature, the Lady form. So this means d bar of this function should have signature q, a pq. So where q is the dimension of the cycle, and yes, and you believe it. You believe this should be true because you see if you have a cycle which is q dimensional, you see its normal bundle. You see its normal bundle going out like this. You see in this direction. You see that's a ball. I'm reasoning only by analogy here, but this is one reason to believe this theory. This is a ball, and you see it's convex in this direction. This is complementary dimension. This should be the convex dimension. Now, you have experience from ampleness in algebraic geometry that if you can move something very much, you should have negative curvature. This corresponds to positivity of the bundle. Yes? Well, here you can move these cycles really a lot. And in fact, yes, you can move them because the thing is cycle connected, so you can connect every point. But I'll tell you, there's a huge difference about moving a cycle just one or connecting a point by 7 moves. There's a big difference, and I cannot prove. I want to control the negative eigenvalues of this. I would like to control Q, and I cannot prove that for what could theoretically happen is so there could be some cancellation in this Schmidt exhaustion that pushes Q down from the point of view of I think that time is more positivity the better in some sense. But and I'm interested here in the negativity of this. Anyway, if you have the Schmidt exhaustion, you can prove that the cycle space is Stein. And there are various ways to prove that the cycle space is Stein. I want to emphasize MD has been shown to be Stein by us. But in general, we do not know that the cycle space is Stein. Because of this problem, we do not have Schmidt's exhaustion in the non-measurable case. And one little project that we're working on is to really see what's happening in the non-measurable case. There are a lot of very interesting things from this motivation. So we only know now that it's a domain and affine variety. It is hyperbolic in the sense of Kobayashi. That's what I just mentioned to you. I don't want to go into the definitions, but just think of it as having a metric of negative curvature, and this is the key consequence for us. The group is a Lie group acting problem. It's the group of holomorphic automosis with a Lie group acting problem. Now, let me comment on that. I will not bother you with bad didactics, but think back of my example of K3 surfaces. Okay. K3 surfaces, we parameterize marked K3 surfaces by a flag domain in a quadrant. Okay. The group is SO319. This group does not act properly on this manifold. This is one of the main ingredients of Griffith's theory, is to have polarizations where you can get some reasonable proper action. This group does not act properly. And you would love for it to act properly because you've done Teichmann theory. If you do the exact same thing for Riemann surfaces, for example, if you parameterize elliptic curves, you get the upper half plane with 1 and tau, and this is the marking of the elliptic curve, and then you mod out by changing marking. That means you mod out by anything that changes tau to another generator of the lattice, and that group is SL2Z, and that group acts properly, and the quotient is the complex plane, and that's the moduli space of elliptic curves, and that's the same thing for Riemann surfaces, except it's much more difficult. In many cases here, and the K3 surface is an example, this discrete group, something like the integral group in SO319, does not act properly. It's very important that it doesn't act properly because there are isotropic groups that are infinite. These isotropic groups have played a role, for example, in dynamical systems. So it's very important that these things are not proper. Now, you want to do automorphic forms. As you know, if you have the upper half plane, if you're understanding a lot of number theory and you want to understand elliptic curves, you need to have automorphic forms of some sort. You cannot have automorphic forms with respect to a non-proper group factor. So my hope is that we should go to the cycle space. We know what it is in principle, and we can compute it in concrete example, where we get the proper action of the group, the discrete group acts properly there, and we can hopefully go back and forth. So I think it's a useful remark. Now, it took me a long time to prove the last part. This is the main theorem in the paper in the American Journal rather recently, that the natural map, in the case it's cycle-connected, then the natural map from the automorphism group or domain to the automorphism group of the cycle space is injective. Not only injective, it's an injective regroup morphism onto a closed subgroup. So you have the best situation you could have hope for. My contribution here is something, but this of course uses a lot of deep classical work on what is a regroup, what is not a regroup, and the topology of the situation. So that's very interesting. You see, believe it or not, this domain, which is more or less an arbitrary flag domain, suddenly has its automorphism group is finite dimensional. Not only that, it's represented here in a natural way in a Lie group, which of course may be much bigger. In general, it is big. Well, as a result, this gives us a complete description of the automorphism group of Lie, which maybe I'll close my talk with that. Let me tell you that description. So, of course, we need cycle-connected. Let me remind you, if it's not cycle-connected, it's a product of a flag manifold over a Hermitian domain. So any mapping of the base into the automorphism groups of the fiber gives you an automorphism group of this total space. So you have this huge infinite dimensional group. So it's a semi-direct product of the good group downstairs and this huge infinite dimensional group. Okay? So you must use cycle-connected. So let's forget that this is cycle-connected. The first remark is the group is cycle-connected. I use this Lie group information to extend it to all of D. Of course, you would guess if I got it extended to all of D, its complexification should be G. In most cases, it is. So there are a few exceptions where it is not. The automorphism group is not G0. The exceptions I won't tell you now, just for fun, because I have a few minutes. You all know the work of Anishi, I suppose. I call it Anishi, but so the question is, given a flag manifold, what flag manifolds have two different complex Lie groups acting transitively? It's a reasonable question. It's the first observation, the parabolic must be maximum. And then there's a case-by-case discussion. His first formulation was for combat, but it's the same. So you check through the case-by-case thing. And, of course, this is the point. Let me just go back to that. Since I can extend the thing to all of Z, that means if I have an exception here to this, I have an exception of the complex group also. So I can just look at Anish's list and see what happens. I was a little bit frightened with this, actually. This required some work. So this is a recent paper that will appear in this records of volume that you, Joe, and somebody else is editing.
Yeah, Jeff Mason.
Yeah, Jeff Mason, which will appear soon, I think. So here are Anish's exceptions. I can go over, but I thought I would list them. So G, for me, is the small group. The easiest example everybody has thought about is the symplectic group on odd-dimensional projective space. The big group is SLNC. And you get into the Cayley numbers of the Artonians. In the other example, the small group is G2, and the big group is SO7, and the ambient manifold is the 5-dimensional quadrant. And then there's this family of examples where I had to work a little bit actually. The small group is SON minus 1, the big group is SO2n. So this has to do with the dn thing at the end. Yeah. This big group is SO2n, and the manifold is the isotropic planes in C2n. So these are the exceptions. And now what I have to do is take every flag domain there and check what happens to the obvious to the real form G0, and whether or not there's a bigger group that acts on that flag domain. There will be a bigger group, or whether or not it stabilizes that flag domain. That's the thing about, I would get new examples. Yeah. So in every case, here's the theorem. There's a uniquely defined real form G0 of G hat, so that the automorphism group is in fact this real form. So it's just, I made the mistake at the beginning of choosing the small real form. But from the point of view of the domain, it's that. And I just for fun wrote here what goes on if you want.
So the domain sort of refers to real form. That's what we should remember.
In every case here, there are exceptions, and there will be two real forms acting transferred on the domain, just like the two real forms.
Yeah, but the domain, okay.
Yeah, that's the way to
The
think.
automorphism group of the domain will be one of them.
Will be one of those. Yeah, of course.
But there is no theory proof, it's case by case. It's case by case, there is no general proof that.
I have no idea how to prove this, Jimmy. So I really had to look at each of these cases. Oh, I started on a general proof here, actually. In this case, it's general, in the projection. But I failed. So in this case, I used something about the Artonians. And in this case, I really used a lot of work. It depends whether P is even or odd, what these various things are. But okay, and you see that there are many. There's a big family here. Because N is varying, P and Q are varying, and depending on that, the signatures vary. Okay. So I was surprised I could do this, but after a little patience, I was able to. And so now the automorphism groups are flying on. It's really an interesting application. I will stop.
There are some questions for our speaker.
A general question about those topics which use slides. Will they be available?
Yeah, it's a good question.
These slides.
Yeah, or the slides from the talk yesterday as well.
Let's discuss this. Dragon is not here, but I would ask for the permission of all speakers who use the slides to give them to me in addition to the text. If you want to, I mean, if you don't want to. But I would hope that you will give me the slides so that we can post it so in the package.
And the video will be available.
Yeah, the video and then the slides. Because I'm not sure from the video how. So I'm asking you to give it to me.
trying to remember the case of K3 surfaces. And you were describing was all K3 surfaces, not necessarily conjecture.
Yes.
And then if you want to talk about projected K3 surfaces with a specific polarization, then someone can go down one dimension.
That's right. The families are 19 dimensions. The families are 19 dimensions. That's right.
No.
So this is, so to make precise the answer, the Kummer surfaces are dense. So a Kummer surface has a meromorphic function on it if and only if the torus has a meromorphic function on it. So I mean, the function field is very close. So almost all of these Kummer surfaces have no meromorphic, or not the furthest possible away from the algebraic. They are, however, dense, and that's a very useful fact you could imagine, because the Kuranishi, there's something called the Kuranishi family. If you start with the manifold, there's a sort of a universal local moduli construction, and Andrade proves that this goes injectively into this library. So if you get, if you know the Kummer surfaces are dense, you start believing a lot of things, and that's somehow how the proof goes. Just historically, it's important. Assume proof that about the same time that we were understanding the moduli, assume proof that K3 surfaces are scalar, and this is a deep theorem. And that is not really used in this construction. And then I think the final steps of the subjectivity of the solving the Torelli problem in that sense of due to Roy Haynes. This is a long history, so I should be
Is it
careful.
possible to say anything about Todorov's contribution?
He had a proof which was not complete.
Are there any other questions? Yes.
So is there any way to check that some metric on some complex space is Kobayashi?
That's, of course, a very good question. What?
Could you repeat the question?
Yes. The question is whether or not a complex space has a Kobayashi metric. I think that's.
No, so assume that you yet have it. How to check is it Kobayashi or not?
You give me a metric,
Yep.
and you want to know whether it is the Kobayashi metric or not.
Yep.
No, there are estimates. You can make estimates. Right?
In your cases, you are not able to really write it down or
No, but so let me. What we are producing here in the ideal world, and in many cases, this is not exaggerated, we are producing a hull of the cyclospace. So the cyclospace, these hypersurfaces are, it's the inside of the complex. So you see all these analytic hypersurfaces outside of the cyclospace, and you remove them all, and then the cyclospace is that component inside. So what you're seeing is at every boundary point, a supporting hypersurface in that sense. And now you build things, now you do complex analysis. You build objects which have pulls on these cyclospaces, on these hypersurfaces. And you construct then metrics using things at that time. Okay? But just think of the example of C minus 3 points.
But in this case, I think you.
I mean, I'm not so sure. Right? I mean, okay, I have a secret metric on C minus 3 points. And maybe it's invariant with respect to something, whatever you can have. Why is it the Kobayashi metric? You see, it's much easier to talk about the Beckman metric because it comes from L2. The Kobayashi metric, again, for people that haven't experienced this, you simply take 2 points, you take maps of the unit disk into this manifold and connect these 2 points by these maps of these unit disks, and then Poincare metric distance is computed that way, and then take the minimum or infimum of all this stuff.
Okay, but the truth is that it's completely unconstructed.
That's out of sight. You could never compute that. That's what you're saying. And I think
Well, it's invariant, so
What?
it's invariant.
That's the key. This is the key point. This is the key point. That's the reason, of course, I went after it.
Any other questions? Then, if I don't see any hands, let's thank the speaker again.